All right, so it looks like half the class is gone, so naturally we'll take attendance. So we're continuing with NP-completeness. We mentioned a bunch of classic NP-complete problems, originally proved by Karp in 1971 to be NP-complete on the heels of Cook's theorem that showed that satisfiability is NP-complete. And so Cook showed that a whole bunch of other, Karp rather, showed a whole bunch of other problems are NP-complete as well, including graph cliques and set cover, when you're trying to cover a bunch of things with the least number of subsets. Hamiltonian cycles, when you want to traverse every node in a graph with a path that touches every node exactly one time. The problem of graph coloring, you want to paint the nodes of a graph with several colors in such a way that no two adjacent nodes that share an edge use the same color. These are all NP-complete problems, like satisfiability. Partitioning, we mentioned that, given a set of integers, breaking it into two subsets that have equal sums. Knapsack problem, how to maximize the total value of a collection of items, given that you have some total overall weight constraint, and each item is, has a weight and a value. The problem of bin packing, squeezing objects into the least number of containers, even the one-dimensional versions, NP-complete, never mind the two-dimensional and three-dimensional and higher dimensional problems of bin packing, such that FedEx needs to solve every single day when they pack packages onto trucks and so on. Steiner trees, how to interconnect things with a minimum number of total interconnect length or wire length or duct length or water pipe length or fiber optic length, whatever it is, the network that you're connecting. Very, very ubiquitous problem. Multiple books have been written on each one of these problems. They're so famous and ubiquitous and practical. Traveling salesperson, of course. You need to visit a certain number of sites, and you want to minimize the total travel time, the total distance traveled, or the total time spent traveling, whatever it is. Again, multiple books have been written about all these problems. Thousands of papers have been written about these problems, individual solutions, heuristics, and I also wrote about these problems over the years. Very, very ubiquitous problems. They're all NP-complete. So these are classical problems, many of which Karp showed that they're NP-complete. So now we're going to take a deeper dive into graph colorability. Given a graph and an integer k, the question is the graph k colorable? Could you paint the nodes using at most k different colors such that different nodes that are adjacent don't share the same color? So obviously you can do it brute force, but that's not the best way to do it. So we mentioned Karp's paper where he lists about 20 different problems, all of which were NP-complete, including the ones we just mentioned and a few others, and since then thousands, literally thousands of problems have been shown to be NP-complete. So NP-complete is not about satisfiability like Cook's first paper kind of alluded to. Cook just found the very first problem that had this property. Karp found 20 more, 21 more, and then now we know there's thousands, and almost every interesting problem that we run into these days seems to be NP-complete or worse. It's amazing we can even do anything efficiently like sorting and searching and adding two numbers together, given that most of these problems that we're trying to solve every day are very computationally intensive. NP-complete or even worse, p-space complete and so on. So that was Karp's paper, early 70s. And we talked about problem transformations, transforming problems to other problems. And today we'll actually see this transformation specifically, among other things, how to convert satisfiability to graph colorability in a way that preserves polynomial time solutions from one to the other. But before we do that, let's talk more about decision versus optimization. So a decision problem has a yes-no answer. So for example, satisfiability can be formulated as a decision problem by asking, given a formula that I give you, is it satisfiable or not? Yes or no? Is there a way to assign the variables that make the whole formula true? And it's always a Boolean answer. The answer is always yes or no, and should always be given, within polynomial time, ideally, deterministically or non-deterministically. But certainly you can do it in non-deterministic polynomial time. But the big question is, can you do it in deterministic polynomial time? But in any case, the decision version is just a yes-no version. So for example, graph colorability. I give you a graph. I say can use 3 colors. The question is, can it be painted with 3 colors, like this example here, where no 2 adjacent nodes share a color? Or clique. I give you a graph, and I say, does this graph here contain a 5 clique? And in this particular example, yes, it does. The green set here is a 5 clique, but unless I painted it green for you or some other color, it'd be hard to tell if it was a very large graph whether it contains a clique or doesn't contain a clique. Now here are the optimization versions of the same problem. So I give you a formula, and I don't want you to just say yes or no, is it satisfiable or not. I want you to actually give me a satisfying assignment if there is one. Given a graph for 3 colorability, I say, here's a graph, give me a 3 coloring, like give me the actual assignments of the colors here that satisfies the constraint that no 2 adjacent nodes share a color. Or if I give you a graph, I say, find me a k clique, in this case a 5 clique, and you come back and say, these 5 nodes here in green are a 5 clique, and I can look at it and say, okay, you're right, I guess, just by checking. So the optimization version actually finds a solution. The decision version just tells you a solution exists. So here's a couple of major theorems about it. One is easy. Solving a decision problem is not harder than solving the optimization version. Because if you give me a solution, I know a solution exists. Why? Because you gave one to me. And if it didn't exist, you couldn't have given one to me. And I can easily see that it's a solution by checking. In the case of satisfiability, I give me a satisfying assignment. You claim a satisfying assignment. Okay, I plug in all the assignment that you give me into the formula and see if it makes the formula true, and then I know that you're right. So if you can solve an optimization problem by handing somebody a solution, they can easily verify that it's correct and agree yes or no that it's a solution or not a solution. So the decision problem is not harder than solving the optimization version. This part of the theorem, the other direction, is the tricky part. This one says, a bit counterintuitively even, that solving the optimization problem is not harder than solving the decision problem conversely. Now, why is that true? How come if you have a decider that just says yes, no, it has an answer, it doesn't have an answer, it has a satisfying assignment, a coloring, this graph has a clique, how can you actually extract the clique from this? And that's a bit of a non-obvious trick, right? But once we establish that, the decision problem will be in P if and only if its optimization version is in P, and conversely, a decision problem is in NP if and only if its optimization version is in NP. In other words, the decision and optimization versions are equivalent with respect to membership in P and or membership in NP. And what this will mean is that from now on going forward, we're talking about NP-completeness, suffice it to just examine decision versions of the problem, not the optimization version. So we'll just care about the yes-no answer. Does there exist a solution or not? And the reason we choose to do that is because it's simpler. The decision version just has 2 answers, yes or no, and that's it. You don't have to hand over a big set of Boolean values or a set of graph nodes for a clique or a set of coloring assignments for a graph. You just say yes or no, and that's it. So now we'll analyze the complexity of decision problems only. But first we have to establish that you can in general build an optimizer from a decider. Okay, and how do you do that? What do you say?
You can call the decider linear times, for example, for satisfiability problem, and give multiple instances every time you change one variable to its negation and give it to the decider.
Yeah, exactly. So if you have a decider, say for satisfiability, and you have some formula, at least P here, some formula, arbitrary satisfiability formula that you're trying to figure out the satisfying assignment for, you can keep asking the decider questions one after the other, isolate each variable, and ask this decider, is P and X satisfiable? And if it says yes, for P and X, you know that the value of X must be 1, must be true, in some satisfying assignment. Otherwise, P and X will not be satisfiable either. So conversely, if P and not X says no, same conclusion. So you can do it either way. I'm just showing you both ways and the equivalence. So if this says yes or this says no for P and X and P and not X, conversely, then either way, X must be true in some satisfying assignment, assuming that the decider always does its job and is correct, which is the basic assumption here. So conversely, if it says no, on the other hand, and P and X is not satisfiable, that means that X is false in some satisfying assignment, potentially, or maybe P is not even satisfiable. But if P was satisfiable and P and X is not satisfiable, then X must be false in some satisfying assignment. Okay. So we assume here that P, the decider said P is satisfiable. Now we're going to P and X. And of course, next step we'll go into P and X and Y. And then later P and X and Y and Z. Of course, if P and X is false, it says no, we'll say P and not X and Y and so on. So basically we're extracting one value, one Boolean value at a time out of this decider to construct a satisfying assignment one bit at a time, one variable at a time. And by the way, if P and X, it says it's not satisfiable, and it also says that P and not X is not satisfiable either, then P is not satisfiable in itself, right? Because you gave it both choices for X and X not. And what if P and X is satisfiable and P and X not is also satisfiable? What can you say about X in some satisfying assignment? It's irrelevant. It's a don't care value. Just like in digital logic design, we have a don't care value. That's what it is here. Okay. So, in general, basically what you've done here is you built an optimizer from a decider. All you had is a decider subroutine that says yes or no. Okay. And from it, by iterating over all the variables one at a time, you constructed an optimizer from the decider. Okay. In other words, finding the actual solution to satisfiability is not any harder than just being able to tell yes or no if a formula is satisfiable or not. You just have to call it a bunch of times. Right? Question.
Isn't it safe to assume that there exists a polynomial solution for that because both are incomplete?
Well, so we're not saying if there is a polynomial time solution to satisfiability or not. In fact, that's an open question. We don't know that. But if there is, there also exists a polynomial time solution for actually finding the answer, not just determining whether it exists or not. So the existence question versus actually finding one are equivalent modulo polynomial time. Either they both in P or they both are not in P. Or they're both in NP or they both are not in NP. But they're bound together now. They're tied together according to this scheme. If one is in, the other is in too. If one isn't in P or in NP, the other one isn't either. Because they're polynomially time related, basically.
Our existing problem that we actually addressed initially, saying that SAT is NP-complete, does not did not say anything about it being an optimizer or it being a decider. So isn't it safe to assume that since both the problems are NP-complete, that there exists a polynomial solution and that would be one of the polynomial solutions?
Well, so both problems are NP-complete. We don't know if either one has a polynomial time solution, deterministic polynomial time.
I'm talking about the it being reducing from one to another. So a decider to an optimizer or the reverse.
Yeah.
We know that the reduction exists in polynomial time.
Oh, yeah, yeah.
So
This is the reduction right here. And the reduction is polynomial time because how many times are we calling the decider inside the optimizer? Linear number of times. So they're not just related polynomially, they're related linearly.
So we can consider that every optimizer and decider has a polynomial time algorithm that can run this way to get an optimizer from a decider.
Yes. Yeah. So that's right. But you have to be careful when we say polynomial time algorithm. This is a polynomial time algorithm that calls the decider a polynomial number of times. But this algorithm may not be polynomial time because this subroutine may not be polynomial time. It just gets called a polynomial number of times. Sure, in fact, just n times. Not just polynomial, but even linear. So it's very low order polynomial. So be careful how you speak about these things. The optimizer may not run in polynomial time, unless the decider runs on polynomial time. But however long the decider takes to run, the optimizer takes only a little bit longer. That's the whole point of this. A couple more comments on this. Most of you have probably ran this algorithm when you were little kids. How many think you've done that? Okay, think about it. Little kids sometimes play a game that basically relies on this algorithm. Yeah, 21 questions or 20 questions. So for example, I think of an object, and you're supposed to figure out what object I think about. And you can only ask yes/no questions. So for example, I may think of an object, animal, mineral, vegetable, I'm not telling you what, right? And you say, okay, is it an animal or is it a mineral? And I say, so you have to ask yes/no questions. So you ask, is this an animal? And I say yes. Okay, your next question might be 4 legs or 2 legs? I'll say 4 legs. And your next question might be?
Is that yes or no questions?
Yes, only yes/no questions.
So you can't answer 2 legs or 4 legs?
Well, so he'll just say, does it have 4 legs? I say yes, 4 legs. So ask me more yes/no questions. So that's, does it live in the water? No, it's not live in the water. It is a mammal, so that's the 5th question.
Does it run fast?
It runs fast? Yeah, it could. That's 5 questions. Bigger than a dog? Yeah, 6.
Does it belong to the cat family?
Cat family? No.
Is it a bear?
No. Well, you don't want to waste your questions that way because you're going to exhaust them very quickly.
How old can it live?
How old? But that's not a yes/no question.
Does it live more than 25 years?
More than 25 years? It probably could, yeah.
Can it be consumed as meat?
Sure. But then
No, but like
most animals can't.
consumed, like generally.
Commonly, no.
Oh, it's a dog.
It's
Is
definitely
it
not
an
a dog.
endangered species?
I don't think so. It's about 12 questions. Is it edible? Yeah. Well, almost every animal is edible, but may not be yummily edible, enthusiastically, by people. Right? People own them. I suppose they could.
Does it have fur?
Is it fluffy?
Fluffy, not so much. I think we're up to 14 questions. Live in the U.S.? No.
I'm pretty sure it's an elephant.
Elephant? No.
Is it Asian? Does it live in sea?
See? No. It's already been asked, actually. If it lives in water, right? No.
Would you be willing to reveal the answer?
Does it live alone?
Live alone? Not so much. It could. Not really.
Does it hunt?
Hunt? No, I don't think so.
Is it Asian?
Is it
Is it Asian?
Asian? What makes an animal Asian? Does it live in Asia, you mean? Is it native to Asia? Probably no. I would say no. Not native to Asia. Yes, it's a zebra. And that took about 20 questions. Now some of the questions were kind of wasted and asked twice about water, so you don't want to, waste questions and that kind of thing. Yes, it was a zebra. Now, how can you guess a zebra out of literally a million different animals? I could have named an amoeba, right? I could have named the Ebola virus. I could have named a big great white whale. I could have named octopus or crab or eagle or fruit fly, or there are millions of species I could have, and yet with 20 questions, you pretty much most of the time will nail it, right? Why does it take only 20 questions? Why wouldn't it take 100,000 questions?
Each question reduces the search space exponentially.
Each question reduces the search space by roughly a half. And so if you have, a million different choices for target animal or object, doesn't have to be an animal. I could have said a diamond, right? Or a roller blade. I could have said a ball bearing. It doesn't have to be animals. But each question reduces the solution space by half. And so with 20 questions, how many objects can you disambiguate, roughly? About 2 to the 20. How much is 2 to the 20 as an integer? 2 seconds, 1 second. Good. You got it. Give you 2-second countdown. So it's about 1 million, right? So it's very efficient, right? And that's exactly what is going on here, right? The optimizer plays 21 questions with a decider. How many can see this? Okay. And this strategy works in general. You can do this not just for satisfiability, but for any problem in NP. Prove to me you can do this for any problem in NP. Reduce the problem to satisfiability and then do this about satisfiability. How would you reduce any problem in NP to satisfiability? Cook's theorem. Yes, my Padawans. Obi-Wan's taught you well. Okay. Any questions about this? Yeah.
Yes, so does the optimizer only give you one solution or a model containing every solution?
So no, we just need one. We're just going after one solution, and one solution is enough. So we just want to know if there's no solutions or if there exists a solution. Often there's an infinite number of, or not infinite, but exponential, could be exponential number of solutions. But that's not particularly relevant to this discussion. There are complexity classes that actually count solutions, like sometimes called number hash, hash p, number p, which is a number of solutions. That's harder. Counting solutions is harder than just naming if one exists or not, because it's hard to tell in general how you would figure out their number without actually going through all of them, and there could be an exponential number. But right now, let's not worry about the number of solutions, just whether one exists or not. Yeah, question.
Is there a parallel between a verifier and an optimizer?
So yeah, they're kind of related. A verifier basically checks whether a solution works. So a verifier typically, so the class NP, there's multiple characterizations of the class NP, all of which are equivalent. So one way to characterize NP is what we've been doing all along. There exists a non-deterministic polynomial time solution or Turing machine that does the job and good. Another way to characterize it is the class of problems for which there's an efficient verifier. Polynomial time by efficient polynomial time verifier. And the reason they're equivalent is to get a problem into NP, you usually can guess and verify it. Guessing is the easy part. Verifying is not that hard either. But a solution is a bunch of satisfying assignments for variables, or a potential bunch of nodes for a graph clique, or a bunch of assignments of colors to nodes for colorability. Guessing is easy. In non-deterministic polynomial time, you can guess an answer to any problem in NP. And then, of course, to make sure you're not stuck in a dead end where your guess is wrong and inadvertently accept when you shouldn't, you got to verify the answer. Checking is also easy. You can easily check whether something satisfies if I give you that solution. Or if I give you a coloring assignment, you can easily check if that assignment actually is a valid colorability assignment for that graph. Or if I give you, a potential clique subset of nodes, you can check if it's a clique by looking if there's edges among all n choose to pair or k choose to pair pairs of nodes from the supposed clique of size k that I gave you. So checking is easy. So you can characterize NP as a set of problems or languages for which there's efficient verifiers. By efficient, again, we mean polynomial time. It doesn't have to be linear, but it has to be polynomial. And there's other characterizations too of NP, all equivalent to one another. Okay, so this is a Jedi trick that always works. It's general, it's ubiquitous, and what it enables us to do from now on, we can just talk about deciders, not optimizers, because whatever you prove about a decider now applies to optimizers too, via this little 20 questions trick of iterating over a decider and thereby yielding an optimizer. Yeah.
Is there a class that you can't get the optimizer from a decider or a polynomial number of queries?
Good question. He's asking, is there some complexity class for which this trick doesn't work, where an optimizer will call the decider a lot of times and it won't be enough, as long as it's a... the short answer is yeah, I think there are. Remember, there's complexity classes that take such enormous amounts of time that, and such enormous amounts of space that this probably will fail. If you insist on only a polynomial number of calls. So, for example, there's problems that take exponential space to solve, and the solution, the optimizer solution, may be exponentially long. So, if you call up decider only a polynomial number of times, it won't do you any good getting this exponentially long answer. Because if you got a brand new bit from decider each and every time without wasting any questions, it'll still only give you a tiny little fraction of the bits that you need to just present the answer to the output. Never mind verifying it or computing it or whatever. So yeah, there's classes like that. But in P and NP, the two are tied together. Yeah.
I was thinking the coloraility says that the decision problem and the optimization problem are hard, equally hard.
Equally hard with modulo polynomial time, yes. Yeah. And again, you have to remember, we're bundling them all together, modulo polynomial time. So P is all polynomial time solvable questions in deterministic polynomial time. NP, the same for non-determinism. Now, it doesn't mean that they're exactly big O notation or theta the same complexity as one another. They may or may not be. So, this may be, quadratic time, and this may be cubic time, but not quadratic time. This may be an omega of n cubed, and this will be theta of n squared. Maybe. That could happen. It doesn't mean they're the same polynomial, although they could be. And sometimes they're not. I mean, even for problems in P, you can do this as long as you say you call this a logarithmic number of times, or something like that, or some sub-polynomial number of times. So computing an answer and checking an answer is not necessarily the same complexity. I'll give you a quick example: sorting. To compute a sorted permutation, how long does it take omega of what in the decision tree model of computation? Sorting requires at least lower bound of what? N log n to sort n numbers. We know that. That's a proof. N log n comparison in comparison model of computation. But if I give you a list and ask you, is it sorted? If I ask you the decision version of this sorted problem, how long does it take you to decide if it's sorted or not sorted if I give it to you? Linear time. But the other one takes at least n log n time. So they're separated. They're not the same complexity. But they're both polynomial. So within polynomial, these two things can diverge. I just give you a provable example where they two do diverge. One is n, theta of n. One is theta of n log n, and one is not the same as the other asymptotically. And you can have more other examples like that. Okay. Any other questions about this? This is a very fundamental principle or a phenomena going on here. So bottom line, going forward, we just talk about decision problems. So now we're going to go through some NP-complete proofs for some of these classical problems so you get the feeling of what these transformations look like. You already seen satisfiability, that was Cook's theorem. Let's look at a few more. So graph cliques. The clique problem is NP-complete. We're about to prove this. And specifically, given a graph and an integer k, is there a subgraph that's basically a k clique? Like here we have a 5 clique in this graph. That's an example. So it's going to be reduction from 3 sat. So we're going to be basically literals will become nodes, and the clauses induce groups of nodes. And easiest way to show it is by example. So for example, here's a satisfiability instance, and I'm color coding it. Each clause will give rise to a set of nodes. So this red clause gives rise to these 3 nodes, x and y and z, corresponding to its literals, variables or negation of variables. The green x, y, and z here, x naught, y naught, z naught, correspond to this green group of nodes. This blue literal corresponds to these three. And now we connect ones that are compatible. So if x is true here, that's compatible with y being false and z being false, and this clause is still okay. It's satisfied. If x not is true here, that's compatible with y not being false, which means y is true, and z is true. So x not is connected to y, and it's also connected to z. Okay, and so on and so on. So all these nodes, all these edges here are basically which variable is compatible with which other variable, clause by clause by clause, all possibilities. Notice that in any red group, in the red group of nodes here, no red node is connected to any other red node. No green node is connected to any other green node. Every colored node is connected to only the other colored nodes, not the same color as itself. So if you have a triplet of variables here, a variable from this group, and a variable from this group, and a variable from this group, it would correspond to a satisfying assignment. So a K-clique will correspond to a solution of this satisfiability instance. So for example, this purple triangle that I'm highlighting now, x and y naught and z naught, there's a clique of size 3, right? It's just a triangle. Corresponds to x being true, y being false, and z being false, because it's z naught and a y naught. And sure enough, if x is true, this first clause is true because x is true. The second clause will be true because y naught is true. That is, y is false. And the third group will be true because z naught is true, i.e., z is false. And so true, false, false for x, y, and z respectively is a solution to this satisfying assignment. And every single clique here is another solution. So asking about how many solutions can you have, one for every triangle in this graph. And there's plenty of triangles. I just highlighted one, but there's another right here. And here's another one still right there. And every triangle here will correspond to a solution. Every solution corresponds to a triangle. And if you want to enumerate all solutions, you can enumerate all triangles, but you could have an exponential number at this point. So what have we done here? We've reduced the problem of satisfiability to the problem of finding a clique. Once you find a clique, you found yourself a satisfying assignment by this transformation. So you've built a graph, you've built a SAT solver, a satisfiability solver, from a graph clique solver as a subroutine. So you've reduced all of NP to graph cliques. Right? Because all of NP reduces to satisfiability via Cook's theorem, and now this reduces satisfiability to graph cliques. And so you compose these two reductions, and you get a bigger end-to-end reduction composed of two reductions. They're both polynomial time reductions, so the whole reduction end-to-end is polynomial, which means all of NP reduces to graph cliques. And this is a polynomial time reduction. This graph is only polynomial size in the size of this formula. Right? Each variable becomes a node, right? Or maybe two nodes, one for the variable, one for the negation, but then the negations have to appear here too. And how many edges can you have in a graph with n nodes or two n nodes? At most quadratic number of edges, right? Every node can be connected to every other node, so it's n choose 2 or n squared roughly. So this graph will be at most quadratic in the number of nodes here, and possibly a lot less than quadratic. So here's a polynomial time reduction. So if you had an efficient graph clique finder, this is how you build an efficient SAT solver from it. How many get this transformation? Okay, so we just proved it's NP-complete. Of course, to completely finish the proof, you have to show that finding cliques is in NP. What's your algorithm for finding cliques if you're allowed non-deterministic polynomial time? 2 words. Guess and verify. 2.5 words. Guess and verify. Okay? So that's it. Any questions about that? So we just proven that finding graph cliques is an NP-complete problem. And a lot of these problems look very innocent. Like, what could be so hard about finding cliques? I'll give you a graph and say, is there a group that they're all interjoined together? Everything's connected to everything else. Well, but how do you know which group to look at? Because there's so many subgroups, there's so many subsets. And you can't possibly go through all of them systematically because that's exponential. It's 2 to the n different subsets among n nodes. And you'd think there should be some sort of a shortcut, right? I mean, there's the clique right there. There's a clique of size 5. Like, why can't you just see it right away in every instance that I give you? Just like you could see it right. Well, the reason you can even see it right there is because I painted it green. And it sticks out because your visual cortex in your head is doing a lot of processing and it's grouping together in your mind all the green things here. But if I give you a general version, it ain't going to be so easy, right? You know, some slides ago, I gave a more, when I talked about cliques, I guess where we started from, right there. So this graph here, if I say, is there a clique of size 4 here? Not so obvious, because I didn't paint it for you. And there's more nodes here, and where would the 4 nodes be? And then for each combination, you have to check if it's a clique or if his edge is missing. And not so obvious now, is it? Because I didn't paint it. And if I give you a graph of size 1,000,000 and ask you, is there a 10,000 clique? Forget about it. You know, this, you can spend eternity, you know, not be able to find this out. All right. Of course, that doesn't mean that in some cases it might be easy. If I give you some big tree, graph that's a tree, acyclic graph, and I say, is there a 3 clique in there? What's your answer? No, of course not. You didn't have to search very hard. Why? Because there's no cycles in a tree. A 3 clique will be at least 1 cycle, 1 triangle. So that's not to say that sometimes you can't take shortcuts. So NP-completeness doesn't mean every single instance will be hard. Just like the halting problem doesn't mean that either. If I say a program is begin-end, obviously it halts. But that's not a general solution to a halting problem. It means a few special cases might be easy, but the problem still is very hard. Same for NP-completeness. And there's research and papers and results about how often these hard instances occur. You can ask very subtle questions about, you know, what's the density of the hard instances over the easy ones? In other words, are most of them hard or most of them easy? And that can vary. That gets much more subtle. Okay, independent sets. Independent set basically is a graph and an integer, and the question is there a bunch of nodes, subset of nodes of size k, where no two of the nodes share an edge. So it's completely edgeless subset of k nodes. In other words, it's an anti-clique. It's the complement of a clique where nothing is connected to anything else. So that's easily shown to be NP-complete. The reduction is from graph clique. We just proved graph clique. Now we're showing graph anti-clique or independent sets. So basically, if you have a solver for clique, you can convert into a solver into anti-clique or independent set, because you can replace edges with non-edges and vice versa. So it's the same set of nodes, but if there was an edge here, here there's no edge. And if there wasn't an edge here, here there is an edge. You just reverse all the edges and non-edges, invert them, negate them. So if there's an independent set here, like these 4 nodes, no 2 of which connect to each other, in the inverted graph, those 4 nodes will be a clique. How many get that? Pretty straightforward. Okay. So if you had an independent set solver, they can convert it to a clique solver simply by negating the graph. The transformation here is trivial. The transformation last slide was not as obvious, but this one is pretty straightforward. So that means in order to solve clique, it suffices to be able to solve independent set, which means clique problem would just reduce the independent set solver, and all of NP then therefore reduces to independent set solving, because Cook's theorem reduces all of NP to satisfiability. The last slide reduces satisfiability to clique, and this slide reduces clique to independent set. So independent set is an NP-complete problem. And of course, it's an NP as well, because verify and guess and verify. Right? So it is an NP, and we just showed everything in NP reduces. So any questions about that? So that was an easy transformation. Yeah.
Does that mean that clique is in NP intersect co-NP?
Yes. But then again, all of P is there, and P and co-NP may end up being the same class. even if P is not equal to NP. So that can happen too. Yeah. All right. So those transformations can get quite tricky. And let me just say that there are transformations, an NP-complete transformation that require hundreds of pages to describe, not just one slide or two slides. They're so convoluted and subtle and complicated, and with dozens and dozens of theorems and corollaries and lemmas that it takes an entire PhD dissertation, an inch thick, just to lay out the transformation. Just be glad I'm not going through any of those in this class. I mean, it'll waste a whole semester basically just going through one of those. So there's no point. So they get arbitrarily difficult and clever. You're basically trying to embed a problem in another problem that doesn't look anything like it. Right? Conway's Game of Life, with these little dots that turn on, that doesn't look like much, but that's a universal Turing machine can be embedded in that game. Strangely enough, the transformation is quite clever actually, and there's really very, very complicated transformations. So now we're about to see a more complicated transformation. This will just take 15 minutes and 2 slides or 3 slides, but I just want to show you something that's not trivial, and then we'll see a couple others that are not trivial, just so you get the hang of it. And so we'll harp on colorability for now. So is the given graph 3 colorable? Turns out it's NP-complete, and we're about to prove it. So we're going to reduce from 3 sat. So we're going to construct a bunch of gadgets that will be pieces of a graph. They'll act as OR gates. For every clause in the 3 sat, x plus y plus z, we'll have a graph piece that would look like this, and it'll act as an OR gate. And this, we call it a gadget because it's like used repeatedly in combination with other copies of itself to produce the final 3 colorable graph that then we try to decide if it's colorable or not. So this gadget is 3 colorable if and only if this this clause will be true. So if you 3 color this gadget, and this is definitely 3 colorable, right? You can use colors blue, green, and red, and this will be green, and this could be blue, and so on and so on. It is easy to 3 color this thing. In fact, there's many ways to color this thing, but it has the property that whatever way you 3 color this little graph here, this color will be the same as one of these 3, at least one of these 3 colors. You can work it out and see that it's true. It's hard to do it on this slide, but play with it and you'll see that this is true. Let me repeat that. This is 3 colorable many different ways. This 1, 2, 3, 4, 5, 6, 7. This 9-node graph is colorable many different ways. 3 colorable many different ways. It's not a unique coloring. But all these colorings, possible 3 colorings of this 9-node graph, has the property that whatever color this gets assigned, at least one of these 3 must necessarily be assigned the same color if it's going to be a valid 3 coloring. And that you can just show by brute force. There's actually not that many cases if you think a little bit more generally about this. How many understand this property? Okay, good. So this color will act as sort of the true color. So we assign the blue to be true, but this is not really blue. The graph is uncolored when you feed it to a decider for colorability. It tells you if there's a coloring or not. The graph is not colored to begin with, right? But whatever color this gets, we'll think about it as the true color. You'll see in a minute where this is going. And if one of these must be the same color, that means one of these is also true. And now this acts as an OR gate. And these are the 3, you can think about these 3 as the inputs, and this is the output. And the output is true if and only if one of the 3 inputs is true, if you interpret the colors in this way. How many understand that? So this is not a real true gate in any kind of VLSI or digital logic design sense. But the colors act and have the same effect as if this was a OR gate. And these 3 things here, the X, the Y, and Z, were the inputs, and that node here was the output. This will come in handy on the next slide. Now, aside from that, for every variable x, we'll create a triangle in this graph such that the x will be connected to the x0, and both will be connected to this 3rd node. So if one of these is blue, This one can't be blue because they're connected together. Every variable is connected to its negation, which will prevent in any three coloring from a variable and its negation to acquire the same color. And both are connected to this, which means this third color, which we'll call green, is not the true or the false color. So there's nothing magic about blue being true. This could have been red, and then red will be true. The colors aren't, blue, red, and green. You could have called them A, B, and C. Or Larry, Moe, and Curly. Or you could call them anything you want. It's arbitrary names, right? But adjacent nodes cannot have the same color, right? That's the big constraint. And separately from that, we're going to connect these three together using these, purple triangle edges that will designate as separate from all the other components of the graph. You'll see in a minute an example. It's probably easiest to show by example. So we'll construct a graph that's colorable if and only if the original satisfiability instance from which we constructed this graph is satisfiable. So if you have a graph colorability solver, automatically that will yield you a satisfiability solver. Here's the example that will kind of tie all these together. So let's say I have this formula here, x plus y plus z and so on, and I'm kind of color coding it. And here are the components I showed you on the last slide. I'm just copying it here so you don't have to go back and forth to the previous slide. Here's all the OR gate kind of components. There'll be several of these. Here's this triangle in purple. Here are all the triangles between x and x naught, z and z naught, and for all the variables x, z, and y, and w, and so on. So here's the first OR gate component. I'm going to color code it red here because it comes from the first clause in this formula. Remember, we're trying to figure out if this formula is satisfiable. We don't know how to do that efficiently, so we'll build a graph that's three colorable if and only if that formula is satisfiable. So if we had a fast graph colorability decider, that'll automatically be exploited by us to result in a fast satisfiability decider. We're going to build a satisfiability decider from a graph colorability decider, which means we're reducing satisfiability to graph colorability, which means graph colorability will be NP-complete at that point. So we're in the middle of this transformation. So this red clause here, x plus y plus z, will translate into this gadget here. And this gadget is the same as that gadget, just a little bit deformed. So it's just topological, so positions of nodes obviously don't matter. It's just the connectivity that matters between nodes. So there's the equivalent of this clause as a graph gadget. The second one, the green one, will be this gadget here. Now the z is already there, so we're not going to reproduce it again. But the x naught and the y naught are two new nodes that weren't there before, so we're going to introduce them now. And all the t's are the same t. So all of them go to the same output t. So it's not separate output t for every OR gate. It's the same output t for all the OR gates, all connected to it. So that's the second clause giving rise to this gadget here. And the third clause gives rise to this gadget there, which is exactly, again, identical to that gadget topologically, right? The x naught and the y are already there, x naught and y. The z naught is not, so we add that in. There's the gadget, the OR gate equivalent. Everything the output connects to is the t, and now we've produced the three gadgets that we are supposed to produce. Now, we need this triangle here, the purple triangle. Where's the purple triangle? Well, t is already there. It's the same t. And we introduce the other two nodes, green and red. Want to see it again in instant replay? Those two nodes will go there. It doesn't matter where you put them. It's topological as long as you connect them in a triangle like I'm showing you in purple. So this long, slivery purple triangle is this triangle here, just stretched out. No big deal. It's topological. It's not geometric. Okay? But what that means is that this value t cannot be the same as this value f in terms of colors in any three colorability of this graph, and both need to be different than the green. So what we're going to do now is connect every variable to its negation and to the green as well. So we connect the x naught, the z to the z naught, and both connect to the green, which means whatever the color assignment of the z is in some color, colorability solution of this graph, some three color solution to this graph, this z must be different than that z naught because they're connected. Both must be different than the green. So both must be either blue or red, but not the same as each other. So you're forcing these input nodes to correspond to truth values in the formula by connecting them just in the right way, constraining way. Okay, and similarly, we're going to connect the x to the x naught, and both connect to the green, which means the x and the x naught cannot be the same color, and both cannot be the same as the green, so they're both blue and red, but one is blue and one is red, not both blue and both red. And similarly for the third node, y and y naught. And so now we have completed the graph, and this graph is three-colorable if and only if this Boolean formula is satisfiable. So I can now try to find a three-colorability assignment to this graph solution, and there's a three-coloring of this graph. You can check that it's a three-coloring because nothing is connected to anything else that has the same color. No two neighbors have the same color. And look how the x and the y, the x and the x naught have opposite colors other than green. The y and the y naught have opposite colors, blue and red. They are both not green because they're both connected to the green, and so and that's how we force the x and the y and the z variables to have only blue and red colors. One will mean false, one will mean true. And because the output is true, one of the three inputs must be true, which means one of these three clauses, each one of these clauses will be satisfied in turn. So this three-coloring of this graph will correspond to the solution x is true, y is false, and z is false. And sure enough, if you plug that solution right here into the formula, x is true, y is false, and z is false, you will get satisfied assignment of the variables here, a satisfying assignment of the variables. X is true, y is false, and z is false. So bottom line is, if we had an efficient three-colorability decider, in this way we can exploit it into becoming for us an efficient three-sat decider that we built from it in this fashion. Once we get this graph going, just feed it to the colorability decider or the colorability optimizer, if you'd like. If you feed it to the decider, it'll tell you if this formula is satisfiable. If you feed it into an optimizer to get a coloring, it'll actually tell you what the assignment is. You can just read it off the colors. Blues being trues and reds being falses. Now, could you have painted this graph in a way that that true is red and blue is false? How many say yes? Yeah. How? Just flip the blue and the red. But guess what? If you flip the blue and the red, they'll flip here too. And this will become red, and now red is true. And this will become red, and now that will be true. That's why we connected the output here in such a way that will make at least one of the inputs the same color as the output, and that's a property of the gadget. How did somebody figure out that this gadget has this property? That if you connect, that whatever output, whatever color this node gets, at least one of these three has that color? Somebody must have sat for weeks or even months back in the 70s playing around with all sorts of graphs and subgraphs and gadgets and testing out the properties and scratching their head a whole lot until they figured this out. This is clever. This is not accidental. This is not obvious. This transformation is insightful, it's incisive, it's clever, it's very deliberate, it's very intentional. It's all those things. Okay? How many get this end to end? All right, good. That's most of you. Any questions? Yeah.
So we have the connection between variables and their negations in order to make sure that they're not colored at the same time. And the true-false coloring that's connected to the green is there for to make sure that both solutions aren't true at the same time.
That's right.
And you have the three different bigger gates for each of the clauses, and that just came out of the template you had at the top.
Yes. Okay. Yeah. So you have all the components here that enforce everything that must happen in this formula to make it satisfiable in a way that this graph is colorable, three-colorable, if and only if this formula is satisfied. This is clever. This didn't have to work, and many other things don't work. that aren't quite this. This takes quite some ingenuity to come up with things. And this isn't even a very complicated, this is a formidable, non-trivial, this is the most complicated transformation we've seen so far. But it's by far no way way up there on the scale of complicated transformation. Like I said, there's ones that take hundreds of pages to describe the entire PhD thesis. This one just takes a couple of pages, a couple of slides, with all the details. Okay. So, let's kind of step back and ask, interesting questions like, what makes colorability so hard? I mean, you can, kind of scratch your head and ask yourself, if you're given a graph, why is it so hard to find out if it's colorable or not? Maybe it's the degree of the nodes. Maybe if you allow the degree to be high, look, the degree of this can be arbitrarily high. The degree of this node could be arbitrarily high. How many get that? The more closures you have, the more the degree. So maybe if you have small degree graphs, maybe the problem will become easier. So now we'll kind of try to explore the boundaries of interactability here with respect to graph colorability. When does the problem become hard? What if all the degrees were small? Like, so maybe a large degree is the problem. Because if you reduce the degrees enough, the problem does trivialize. Right? If you have max degree 0 graphs, where the degree is at most 0 everywhere, is it 3 colorable? A graph like that is 3 colorable? Max degree 0. How many say yes? What's your algorithm to determine if it's colorable or not, if the max degree is guaranteed to be 0? Just say yes, and you'd be right. That's very simple. One print statement is the algorithm. Just say yes. So you see, if you reduce the degree enough, it becomes trivial. Here's a less trivial example. If the degree is at most 1, is it 3 colorable? So that's trivial than 0, but not that hard to begin with. Yeah, not necessarily even a forest. It's simpler than that. Because if you have a chain of 2, if you have a chain like this, the degree here is 2, not 1. So it'll just be pairs, either isolated nodes or pairs. So yeah, of course it's 3 colorable. It's the same algorithm as before. The answer is yes, it's 3 colorable. But more than that, what's the maximum number of colors necessary? 2, not even 3. 2 suffice. For the 0, how many colors do you need? 1. Here's a even less trivial example. Max degree 2. What's your algorithm now? I give you a max degree 2 graph and ask you, is it 3 colorable? I'm going to say max degree 2 graph is always 3 colorable. How many say it's always 2 colorable? How many say it's not always 2 colorable? So well, some people are voting twice. We have a split vote. How many say it is always 2 colorable? Okay, still a split vote. Interesting. I mean, it's a class full of smart graduate students, and a split vote. That means somebody will learn something in the next 30 seconds, right? For a change. So tell me, which one is it? Not always 2 colorable. When is a max degree 2 graph not 2 colorable?
There's odd number of
Odd cycles. So think about a triangle. A triangle, degree 2 everywhere. Not 2 colorable. 3 colors are necessary because it's a 3 clique. Right? Give me a general characterization of a class of all graphs that have max degree 2 and are not 2 colorable.
a ring that has odd number.
3 clique. So he's saying a graph is max degree 2 and not 2 colorable if and only if it has a 3 clique. How many agree with that? How many disagree? So a lot of people disagree. So what do you guys say instead?
Any graph having a cycle with odd number of nodes.
Any odd cycle, not just size 3. Because if you have a cycle of size 5, same problem. Color 1, 2, 1, 2, 1. But there's a 1 next to a 1 now. Any odd cycle will foil at 2 coloring. And a third color will be necessary when we try to close the loop. How many see that? So a max degree 2 graph is 2 colorable if and only if it has no odd cycles. That wasn't trivial. But if you think about it, yeah, that's pretty much it. That's a condition. So what does a graph look like if it has max degree 2? What is its structure in general? So you can have odd degree cycles, even degree cycles. Anything else? Chains. Long paths. Could it have a tree? I would say, yeah, it can have a tree. Think again. Like a binary tree. What's the degree here? 3. Right? Degree here is 3. Right? 1, 2, 3. Right? A parent and 2 children. That's degree 3. Right? Nuclear family. Right? So you can't have trees. You can only have chains or cycles. That's it. That's what these graphs look like. Chains, how many colors required for chains only? 2. For cycles, 2 if they're even, 3 if they're odd, but never more than 3. So any max degree 2 graph is 3 colorable, and many of them are 2 colorable, and it's easy to tell which is which. Look for odd cycles. All right, here's a big theorem. Max degree 4 graphs, NP-complete. And notice that I skipped max degree 3. Extra credit, you tell me if max degree 3 is NP-complete or not. But we're about to prove that max degree 4 graphs is NP-complete to determine 3 colorability for them. So what are we saying? We're saying that if you reduce the problem parameter of max degree enough to 0 or to 1 or to 2, the solutions are trivial in deterministic polynomial time. Look for odd cycles, look for chains, look for any nodes to find degree 0, any edges or lack of edges. Anyway, you can solve the problem exactly for degree 0, for degree 1, for degree 2, max degree 2 graphs. For degree 4 graphs, that's where it explodes. There's something magic about degree 4. So we're about to show that graph colorability is NP-complete for max degree 4 graphs. And why are we doing this before we even do this? Why are we doing this? We're trying to figure out the threshold of intractability. We're trying to figure out the subtle point where it goes from trivial to incredibly complicated. And it happens very abruptly. There's a phase transition here. Okay, so we're looking for these phase transitions where it goes from trivial to horribly complex, to full-bloomed NP-completeness. It happens at 4. For other problems, it happens at different numbers of parameter, whatever the parameter is. Okay, for colorability, it happens at 4. All right, so the proof is not going to be easy. It's going to take a couple slides. So we're going to have a degree reduction gadget. So again, it's a gadget-based proof. We're going to do substitutions and replacements using gadgets. And this gadget, it looks like this. This is a fixed gadget. It's a piece of graph. We're going to use this multiple times, just like we used that OR gadget multiple times in the previous reduction from SAT to colorability. And this gadget has the following properties. It's max degree of 4. How do we know? Well, just look at all the degrees. It's 4 all the way here and here and here and here and here, and it's 2 over on the corners, but certainly doesn't have degree 5. That's what we're saying here. It's easy to see. It's 3 colorable, but it's not 2 colorable. How do we know it's 3 colorable? Well, here's the 3 coloring of it. There's others too. It's not of course, no coloring is unique. You can always swap colors around, for example. Just substitute colors for other colors. How many get that? You can always swap colors. You just rename the colors. Right? Instead of calling them blue, red, and green, call them alpha, beta, and gamma. But it's not 2 colorable. Why is it not 2 colorable? Why is this gadget? Because it has a 3 cycle. We already said 3 cycles foil 2 colorability. Here's the property that's not the least less obvious. Any 3 coloring of this gadget leaves all 3 corners, the 3 corner pieces, this one, and this one, the 3 corner nodes, all get the same color in any valid 3 coloring of this entire gadget. Let's prove that separately. That's an important property, as you'll see in a minute. If you have this piece of graph here, and I'm 3 coloring it, this node and this node must get the same color. These two opposite ends of the diamond here must get the same color. How many get that? Because this and this and this must all be different. And this must be different than these two, and this must be different than these two, and these two already take two colors, and the third color must hit this and this simultaneously. And so two opposite sides of a diamond, whenever you have a diamond configuration like that in a graph, must have the same color. So keep that in mind. Right? So basically what we're saying is that this red can force this to be blue or green, and if this is blue, this becomes green. And if this is green, that becomes blue. There's only two choices there. But whichever way it goes, this one is forced to be red by these two being blue and green. So you can think about it as degree propagation constraints, or degree or constraint propagation via, colorability constraint. Okay. In other words, these two opposite diamond tips must have the same color. All right, here comes the gadget. We're going to use this lemma as to show that all three corners in this gadget must have the same color. So this middle color, it doesn't matter what color you assign, right? You can assign whatever color you want to this middle node. Call it red. If you assign blue, that's fine. But here's a diamond. So whatever color this is will propagate to here via this argument. How many get that? And here's another diamond. So whatever color is here will propagate to here. Whatever color is, so now these two must be the same. There's no diamond because it's missing the crossbar. So we're not done yet. But this will propagate that color to here and to here. We're getting there. And so these two must be blue and green or green and blue. How many get that? Which one should we chase? It doesn't matter. Why? Without loss of generality, we can make this blue and this green rather than this green and this blue. Why? Because it's symmetric. If we make this blue and this green, flip it around, and now you got the other one. So we only have to chase one of them and not two. How many get that? Okay, because it's isomorphic, right? So make it, without loss of generality, blue and green, not green and blue. Because the other one is just flip it around. But now we have other color propagation constraints, right? These two force this to be green, because there's a triangle. Right? These two force this to be green, to be blue, because that's a triangle. Right? And now these two, being a neighbor of this, force this one to be. These two force this one to be red. Oh. Yikes! And there you have it. So we proved that this color in the middle propagates to all three vertices in any valid three coloring of this gadget. Okay, so we proved these three properties. Any questions so far? That's just a lemma in this bigger theorem that max degree 4 graph colorability is NP-complete. All right, now we're going to exploit this gadget that has these properties in the following way. We can combine copies of the gadget into larger gadgets. So this one copy of the gadget has a property that all three corners must have the same color. What if we double up the gadget like that? And even triple up the gadget like that? These external nodes will still have the same color as each other. How many get that? Yeah. Because it's overlapping on these edge nodes. But look what we're going to do from this. First, we note that the three properties that the gadget had over here, if we double it up like that, these properties remain the same. They're invariant. Why? Because this super gadget has max degree 4. How do you know? Well, count it. It's never, we haven't increased the gadget degree simply by overlapping it. We kept the max degree to be 4. It's 3 colorable, but not 2 colorable. Here's a 3 coloring of it, but it's not 2 colorable because it has lots and lots of triangles. Odd cycles, right? And in any 3 coloring, all the corners here that I'm painting, that I'm highlighting in dotted lines, have the same color. Okay, so we're going to use these super nodes or super gadgets as fan-out components to reduce high degree nodes into low degree nodes and still maintain the colorability of the resulting graph after these substitutions. Let me show you how that might work. So here, let's say graph has a high degree node somewhere, degree 5. By high, I mean higher than 4, because we're trying to show max degree 4 graphs are NP-complete with respect to colorability. So I'm going to locally replace high degree nodes with lower degree nodes. How? Take this high degree node, blow it up like this, and these 5 edges still are there, and they're connected to whatever they were connected here. So I'm just kind of blowing up that node. But instead of having that node there, I'm going to have this super gadget there and connect these 5 incoming arcs to corners of the super gadget. And the super gadget will still have max degree 4, right? Because it had max degree 4, and these new edges connected to only the corners will keep the degree less than 4. In fact, these degrees will be 3 only, not even 4. But all these 5 nodes here must have the same color as each other in any 3 coloring of the entire graph, this piece plus whatever the rest of the graph looks like. In other words, these 5 incoming edges feel the same color, sense the same color going into this, to this abstract node, which is really a gadget, a super gadget replacing the original node. So color constraints will still be propagated exactly the same way in this graph as they would in the original graph before this substitution. How many see what's going on here? Good. It's a lot of you. So here's what it looks like for an example. Let's say you have this graph, you're trying to find out colorability for this. You don't know how to do this because it has high degree, and you only have a degree 4, max degree 4 colorability solver, not a max degree 6 or anything higher colorability solver. So what do? You take this high degree graph, and wherever the degree is more than 4, you take these nodes out. So we'll surgically amputate these nodes, remove them from the graph like that, and instead I'm going to replace that gadget there. So let me do that. There's the gadget. And I warped the gadget so it fits into the circle, so it's not, it doesn't go off the screen. But now connect these 5 incoming, or rather it's 6 actually, 6 incoming edges to the tips of this gadget. Connect it to here, and 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 to here. I just love PowerPoint. I don't know about you, but now this graph is 3 colorable if and only if this was 3 colorable. How many get it? Good. Except that this graph has max degree 4 around this neighborhood. Here it says max degree 5 right there. So what do? Same thing. Replace that node with another gadget, and that'll fix that degree and reduce it from 5 to 4. Right? And this gadget will only have 3 copies of the gadget. Here we needed 4. And if you have a degree 20, you need 20 copies of this gadget all in a row. Same principle. So the max degree now is 4, and this graph is 3 colorable if and only if this was 3 colorable. And now we can feed this graph to a max 4 colorability solver that doesn't have to bother with graphs of higher degrees at all. And still, this will tell us if the original graph was colorable or not. And we already know, if we wanted the actual coloring, how do we get the actual coloring besides being told that it is 3 colorable by this 4 degree max degree solver? Yeah. So you can. We already know how to convert a decider into a solver in general. So you can do that if you really want the answer. But so this is a proof that max degree 4 colorability is NP-complete, not just general graph colorability. This is highly constrained colorability, right? And this was a transformation. This was the F, this was A, this was B, and this was the F, transforming this into that. Remember the A and the B and the F? How do you remember that? Okay, the reducibility diagram. This is a special instance. This is a particular instance of applying this general reduction of A to B via F, and F is polynomial time. Right? How do we know it's polynomial time? You're not increasing the graph size by more than a polynomial, right? Every node of high degree becomes a linear number of gadgets with a constant number of nodes in each, 1, 2, 3, 4, 5, 6, 7, 8, multiplied several times based on a degree. But the degree You know, so this graph is linear in the size of that graph. Never mind polynomial. How many get that? And even if it was quadratic, it'd still be okay. But it's not even quadratic. So the conclusion is that solving max degree 4 graph colorability is as hard, is as difficult as solving arbitrary graph colorability. And yet, it's just max degree 4. Remember, max degree 0, 1, and 2 were easy. Max degree 4 is already NP-complete. I'll leave it as you as an exercise, extra credit. Tell me what about 3. So we know 0, 1, and 2 are easy. 4 is arbitrarily hard, NP-complete. 3 is still not resolved in this class. I mean, you know, we know what the answer is as a field, but for extra credit, try to figure out the case of 3. Now that you see how it goes. Any questions about this? So this, I guess this took 3 slides. I mean, this is formidable proof because it involves some cleverness about first, somebody had to come up with this gadget and nail down its properties to make this work. How did they do it? Well, a lot of trial and error, a lot of cleverness, MacGyverishness. They probably tried dozens or even hundreds of other gadgets that didn't work, and this one works. It's generally not easy to come up with these transformations. Some are easy, right? You know, so in cliques to independent set, that was just negating the graph. That was an easy transformation. This one's not so easy, right? And any other questions or comments so far? So we're proving more and more problems are NP-complete, and incisively, we now know it's not about the degree. The degree doesn't matter. Even small degree 4, it's still a very hard problem, which is nice to know, because you might think maybe it's about the degree of the graph. And when we come back from the break, we'll prove a follow-up theorem that shows it's not just about the degree, that it's not about whether the graph is planar or not. Even for planar graphs, it's still NP-complete. In fact, even for planar graphs of max degree 4, it's still NP-complete. And we'll talk about that. You know, it'll take some doing. This is a kind of a preview of what's going to happen. Planar graph? Good question. What's a planar graph? Anybody want to answer that? A graph is planar if and only if. You can draw it on a plane without any 2 edges crossing in the drawing. Now, some planar graphs you can draw with edges crossing, but you can also draw them in another way without edges crossing. So you have to draw it in the plane without any edges crossing. So, for example, if I have a 4 clique, try to draw it without any edges crossing. So here are the first 4 edges. Here's the 5th, and the 6th can be drawn here, but that will cross this edge. So I'm not going to draw it here. Where will I draw it? Go around. So here's a planar drawing of a 4 clique. So a 4 clique is a planar graph because there is a way to draw it without anything crossing. A 5 clique is not a planar graph. Try however you want to draw a 5 clique in a plane without 2 edges crossing, you will fail. There is no way to draw it in a plane without 2 edges crossing. There's a famous, again, a children's kind of a riddle showing, 3 homes, I don't know, like this. I don't know. Now you know why I'm not an artist, but rather a computer scientist. All right, this was better. And 3 utilities like some water utility, electric utility, and I don't know, phone. I'm going to draw old-fashioned phone. Phone utility. Something that let's just draw a smartphone as because phones. Yeah. So as phone utility, and each house has to be connected to all 3 utilities without any lines crossing. Assuming these are landlines, okay, old-fashioned phones. So you can connect the first house, to the first 3 utilities. That's fine. You can connect the second house. Now you can't cross, so the second house can connect to here. It can connect to here, and it can connect to here, right, without anything crossing. It's getting more and more constrained, you see. The third house, we're going to be in a bit of a trouble, right? You can connect, the first to here, the second there, but now you have to connect this house to this utility, and there's no way to do it. Now you might think, well, what if you try some other, scheme? Nothing will work, turns out. And you can show that K33 is not planar. This will be the complete bipartite graph on two sets of three nodes. So we already mentioned that K5 is not planar. And now we're saying K33 is not planar. And it turns out there's a famous thing by Kuratowski that says a graph is planar if and only if what? If anybody happen to know it or heard of it? A graph is planar if and only if it doesn't contain either one of these two graphs as a subgraph, as a homeomorphic subgraph. It doesn't necessarily have to be exactly that. If it contains a graph that looks like this and has an extra node here and maybe two nodes here, that's homeomorphic to a K5. So you can have extra nodes, but so this and that are the two pitfalls for planar graphs in 2 dimensions. Now, strange things happen if you're not in the plane, but on other manifolds, on other topological manifolds, like spheres, donuts, double donuts, projective planes, Mobius strips. But we'll talk about that after the break. So now we'll talk about planarity and colorability with respect to planar and non-planar graphs. You'll see we're going to prove that planarity is not the issue either. For planar graphs, it's still NP-complete. Okay, any other questions before we take a short break? All right, so let's regroup in about 15 minutes, and we'll keep going with NP-completeness and colorability. K33 is the bipartite graph on 3 and 3. So, yeah, bipartite, which means every node here is connected to every node there and vice versa, but not to each other. That's all.